Hi everyone, I'm Mr. Fullerton, and I want to take a little bit of time today to go over a tutorial on electrical energy and power. Our main objective is going to be to calculate the power and the energy used in electrical circuits. So let's dive right in. Electrical power is the rate at which electrical energy is expended. So power, which is a measure of how quickly electrical energy is used, the rate is equal to the work or the energy in joules divided by the time in seconds. And the units of power are going to be watts, just like they were when we talked about mechanics. So that's a joule per second. But power is work over time, or energy over time. We also know that electrical energy is charge times potential difference divided by time. So another way we could write this equation. But if we rearrange this a little bit, that's charge over time times potential. And if you remember, charge per unit time, that was our definition of electrical current. So that's equal to current times potential difference. Now, if we also apply Ohm's law, remember that V equals IR. So we could write this as I squared times resistance. Or, since I is equal to V over R, that's also equal to V squared over R. So we have a bunch of different ways we can calculate the power for an electrical circuit, the rate at which electrical energy is being used. Of course, conservation of energy still applies, so the energy used in any sort of resistor is going to be converted into heat and light, or it can be used to do work. Let's see if we can't put this knowledge to use in a couple of practical examples. A 110-volt toaster oven draws a current of 6 amps on its highest setting as it converts electrical energy into thermal energy. What is the toaster's maximum power rating? Well, its potential difference is 110 volts, and its current at its highest setting is 6 amps. What is the toaster's maximum power rating? So we're looking for power. Well, since I know potential difference and current flow, I can say that power is just potential difference times current flow, 110 volts, times 6 amps, which is going to be 660 watts. Very straightforward calculation. Let's check out another one. An electric iron operating at 120 volts draws 10 amps of current. How much heat energy is delivered by the iron in 30 seconds? Well, now we're going to realize that we have a potential difference of 120 volts. Our current is 10 amps, and this is going to occur in a time of 30 seconds. We're looking for heat energy delivered. So that's going to be energy, in this case, capital W, the electrical energy. Well, work, if you recall, is power times time, and power is current times voltage. So that's going to be VIT. Or when I substitute in with units, 120 volts times 10 amps times 30 seconds, or I come up with the total amount of energy of 3.6 times 10 to the 4th joules. Just another manipulation of our basic equations for power and energy. Here we have a question on units. 1 watt is equivalent to what? We've got a choice of a Newton meter, Newton per meter, a joule times a second, or a joule per second. And if you recall, a watt is a unit of power, and power is work or energy divided by time. Units of work or energy are joules, time is in seconds, so a watt is going to be equal to a joule per second. 1 watt equals 1 joule per second. Therefore, our answer must be choice 4. All right, moving on. We have a potential drop of 50 volts measured across a 250 ohm resistor. What is the power developed in the resistor? Well, power again, we have a number of different equations you can use for it. One of them is potential difference squared divided by resistance, or 50 volts squared divided by 250 ohms, should give us a power of about 10 watts. Another manipulation of our basic equations. What is the minimum information needed to determine the power dissipated in a resistor of unknown value? And we've got a lot of choices here. Potential difference across the resistor. So if I know just V, I don't think that's going to do it. Current through the resistor, I. Well, with just current, I can't figure out the power dissipated. Current and potential difference only, VI. Well, that should work because if you recall, one of our formulas for power is power equals potential difference times current. And finally, current, potential difference, and time of operation. Well, yeah, that would work too, but that gives us more information than we actually need. So our best answer here must be choice 3. Hopefully that'll get you started on calculating power and energy in electrical circuits, and you can find tons more examples, get more help on aplusphysics.com. Thanks, and make it a great day.